Hello, sir.
Yeah,
Yeah, start your presentation, sir.
okay. So, hello and welcome, everyone. And I'm Chenzhe Wu, and I'm here to present our research on effective data transmission in NDN-assisted edge cloud computing model. And this work is a collaborative effort with my crew, Boan Shi, Jiaxin Huang, and Arijit Karate. Recording in progress. From the Taiwan National Sun Yat-sen University Department of Computer Science Engineering. And this study will focus on enhanced data transmission efficiency in the context of IoT and cloud computing using named data networking and edge computing. Okay, so in this presentation, we'll go through several sections, starting with an introduction, and we'll discuss the current challenges in internet data transmission and how our proposed data addressing this issue. And we'll explore named data networking and its significance, followed by the operational mechanism and data authentication methods in NDM. And our research methodology encompassing the NDN system architecture and the model we developed. So this discussion will then lead us to the results and their implications. Finally, we'll conclude with our finding and look ahead at the future work in this domain. Uh, in the introductory section, we aim to talk about the evolving landscape of the internet, especially with the proliferation of IoT devices. And this evolution represents a challenges in data storage and processing. Like traditional cloud services are increasingly facing issues related to storage capacity, security, and efficiency. And in this context, we propose a approach using named data networking and edge computing, which could potentially revolutionize how data is transmitted and accessed. So, uh, so the internet's rapid growth, coupled with the exponential rise of IoT and smart devices and the media streaming, has led to an unprecedented data demand. And this surge has stretched the existing cloud services to their limits, revealing critical shortcomings in storage capacity, security, and overall efficiency. So our research is focused on is focusing on addressing these growing pains. And moving on to the core concept, named data networking. So NDN offers a paradigm shift by focusing on data contents rather than the host servers. So this approach aligns well with the emerging demands of modern network environments and coupled with edge computing, which process data closer to the end to the source. So this efficiency of data transmission can be significantly enhanced. And in this slide, figure number two illustrated the conceptual framework of the integration. So So moving on to the core concept, named data networking offers a is a proposed edge NDM model. So our proposed edge NDM model is synthesis of NDM and edge computing. This model aims at reducing dependency on cloud-centric architecture and improving overall data transmission efficiency, and the benefits are manifold, like faster data access, reduced latency, and enhanced user experience. So in the literature review section, we will explore the existing body of work around NDM, its relevance in the current technological landscape, and how it operates at the node level, We'll also examine the methods of data authentication within Endian, setting the stage for our research methodology. So this slide compares the architecture of traditional internet and Endian. The key difference includes the TCP/IP protocol in conventional internet architecture versus the internet data, interest data net, IDN, and content store protocol (CSP) in Endian. These differences show the shift from host-to-host communication models to content-oriented models central to our studies focus. And in discussing the operational mechanism of Endian node, we underscore how these nodes process data and interest packets. And this approach is different from the IP-based processing in traditional system and leads to more efficient data transmission and retrieval as illustrated in our model. So this part will talk about the data authentication in Endian. So data authentication is crucial in Endian. Endian utilizes data packet names and key locator for secure and efficient verification. And this ensures the integrity and the reliability of data transmission in our edge Endian model. Okay, so our research methodology involves constructing a system architecture and that marries Endian with edge computing. And this architecture facilitates local network search for data, reducing the frequency of cloud server connections and diverging the caching and edge node for quick data retrieval. So in this section, we look deeper into the system architecture and its operational specifics. And aspect of our research was the adoption of client control strategy for packet delivery. We chose this strategy because it effectively addresses the challenges associated with handling null data packets, a notable issue in the broadcast strategy. And moving on to the process flow within the Endian architecture, when an interest packet reaches an Endian node or an edge node, the process is systematic and efficient. Firstly, the node stores the received interest packet in its pending interest table, so commonly referred to as the PIT. And the node then proceeds to check its content store, abbreviated as CS, for the requested data. So this is where the efficiency of our model becomes evident. If the requested data is present in the CS, the node swiftly deletes the corresponding interface in the PIT, and subsequently it sends the data back to the requester, so completing a successful data retrieval cycle. But however, in scenarios where CS doesn't contain the requested data, our model employs an approach we utilize Endian tools command for these situations. And these commands will request and wait for the desired data, ensuring that the system remains responsive and efficient in data retrieval. And even when immediate data availability in the CS is lacking. So in our system model, we outline the roles of clients, edge nodes, and the Endian layer. So clients interact with edge nodes to access the Endian layer, where data packets are named, authenticated, and managed, ensuring efficient and secure data retrieval processes. So now let's focus on the endian layer. A feature that at this level is the use of authenticated keys in data packet names. This is a strategic approach to enhance data security and integrity. So each data packet name ends with an authenticated key, which plays an important role in the data transmission process. The primary function of this key is to ensure that return data packets are routed correctly back to the user. And this mechanism is for maintaining the integrity and accuracy of data retrieval process in our model. So, like in figure 5, node number 2 and 4 are demonstrate this process in action. Um, These nodes append unique keys to their interest packet, and these unique keys are not just identifiers, they are pivotal in guiding the return data along the correct path back to the user. So in this part, moving to the edge cloud integration. So in our system, when nodes are unable to locate the required data within their local resources, they turn to the edge nodes, and these nodes serve as a gateway to the resources of cloud services, bridging the gap between the local and the cloud storage. So in the model, in the figure 5, you can see the nodes number 3, 5, and 7. Um, are configured to have direct connection to the cloud services. And this direct connectivity is not just a matter of linking to the cloud, it's about optimizing the data retrieval process. And each of these edge nodes is equipped with forwarding information bases known as FIBs. And these FIBs are not the ordinary routing table. They are designed to have exclusive paths leading to their respective cloud services. So next, in this section, we'll present our findings and discuss the implications of the results. So we'll briefly explore our experimental setup and objective. Our setup involved virtual machines on a single Ubuntu host, comprising client servers functioning as endian level nodes, and endian
recording stopped.
And endian nodes to connect. And endian nodes connected to the cloud. This setup was important for realistic testing our model. And let's see the specific execution scenario we tested in our experiment and the result we obtained. Let's go through each scenario. So the first scenario here, all the nodes in the system lack a requested file, and the result was that retrieving a file from the cloud, it took 1.547 seconds, and this time frame represents the efficiency of direct cloud access in our system. And the second scenario tests the system's local data retrieval efficiency. And the edge nodes directly connected to the user already has the requested file, and the result was impressive. And the file was received from this connected edge node in just 5 milliseconds, demonstrating the speed of local data access in our model. And the third scenario, in this case, the requested file resides in the edge node farthest from the user. This scenario tests the efficiency of our system data retrieval over a longer path within the network. The file was successfully retrieved from the farthest edge node in 137 milliseconds, showcasing that the system's effectiveness even when the data is not immediately adjacent to the user. So in conclusion, our study illustrated illustrates the potential of integrating NDM with edge computing for efficient data retrieval within the edge cloud computing paradigm. We look forward to build upon this work to further enhance the security, scalability, integration, and the performance aspect of the edge NDM architecture. And these are the references. And thank you all for your attention.